Okay, so this is 2011, step 1, question 1. So show that the gradient of the curve a on x plus b on y equals to 1, where b is not 0, and the gradient would be ay squared on bx squared. Fine. Okay, so when we find some gradients, the obvious way to go for it is to differentiate and to get the gradient function. Fine. Okay, so let's do that. So we need to do implicit differentiation this time because we don't have y isolated just yet. So if we implicitly differentiate, what do we get? Okay, so let us write the equation in a slightly different way because I enjoy the product rule much more compared to the quotient rule. So if I differentiate plus b minus 1y to the minus 2, remember implicit differentiation, you need to put dy by dx when you're differentiating in terms of y equals to 1, no, equals to 0 actually, because 1 differentiates to 0. Fine. Okay, so we simplify. So that's a on x squared, subtract b on y squared, dy by dx equals to 0. Fine, so I have to isolate the dy by dx now. So simply just put the a on x squared to the other side, and you will get the answer here. That'll be ay squared on bx squared with the negative. Fine, okay, so that's the first line of the question done. Lots to go. So the point PQ lies on both the straight line ax plus by equals to 1 and the curve we had just now, where AB is not 0. Given that at this point the line and the curve have the same gradient, show that P equals to plus or minus Q. Okay, so they have the same gradient. So if I substitute PQ into their gradient functions respectively, then I should get the same expression. Okay, because at PQ they have the same gradient, so the expressions have to be the same. Okay, so I have to differentiate the ax plus by equals to 1. So ax plus by equals to 1. If I differentiate that, I get a plus b dy by dx equal to 0. Yeah, and isolate dy by dx. So dy by dx would be minus a on b. Okay, that should be easily seen. Okay, so I have to equate the expressions, and remember I have to sub in P and Q as my coordinates. Okay, so minus a on b is equivalent to minus ay squared on bx squared. Fine, so the minus a on b's cancel each other. So 1 equals y squared on x squared. Well, I should sub in P and Q first, shouldn't I? So let's not get rid of the minus a on b just yet. Let's substitute first. Okay, so minus a on b equals minus ay squared on bx squared. Okay, so minus a on b equals to minus a q squared on b p squared. Okay, now we could get rid of the a on b. So 1 equals q squared on p squared, such that p squared equals to q squared. So the result follows. P equals to plus or minus q. Okay, good. So we have got more of the question done. So we'll move on to the next bit. Show further that either a minus b squared equals to 1 or a plus b squared equals to 1. Okay, so in step questions, all right, it's always wise to think about how we could use the information in previous results that we've got from the question, because it's probably relevant, right? So we know from the last paragraph that P equals to plus or minus Q. All right, so we might be using that fact here. Okay, so because PQ is a solution to the two equations there, right? Because it says the point PQ lies on both the straight line there and the curve there, right? Okay, so PQ would be a solution to the simultaneous equations where we have ax plus by equals to 1 and a on x plus b on y equals to 1. Fine, so let's subdivide in two cases because we have two cases, right? So p equals q or p equals minus q. Okay, so if we put in p equals to q, so we could have ap plus bq. Okay, this is common to both cases because I'm just subbing in p and q first. Okay, so this is common. Fine. But now we need different approaches to solving the simultaneous equations because p and q have different relationships. All right. So let's say p was equal to q. Okay. So if p was equal to q, what do we get here? So if I sub in, let's say I sub in p equals to q to here. So aq plus bq gives me 1. And what do I have here? And aq plus b on q equals to 1. Fine. So if I have these solutions here, no, the pairs of equations here, so I could have a plus b equals to q squared. Yep. No, aq plus bq equals to q squared. And from the first equation, I have q brackets a plus b gives me 1. Yep, happy with that? Yep, okay. So the next bit we could get is, so we know aq plus bq is equal to 1 from the first equation. Yep, so we could deduce that q squared equals to 1. And if we look at the second equation that we have got here, if we square the equation here, then we get q squared a plus b squared equals to 1. Okay, we're just attempting to solve the equation basically. Okay, so q squared equals to 1, so that basically does nothing. So a plus b squared would equal to 1. Yeah. Okay, so a plus b squared equals to 1 there. So that's the result for a plus b squared. Okay, so we have to do the same for p equals to minus q. Okay, so same thing. We have to put in ap minus bq equals to 1, and a over p minus, no, let's use q, shall we? Or should we use p? Let's use p. So I erased all of that. So ap minus bp equals to 1, and a on p minus b on p equals to 1. Fine, and we have to basically do the same thing as we did just now with p equals to q. Okay, so from the first equation, no, from the second equation actually, from the second equation, if we multiply through by p squared, well, or p itself actually, so that would be a minus b equals to p, right? And we could factorize p from the first equation, so p brackets a minus b equals 1. So if we sub that in, so a minus b equals to 1 on a minus b, which gives a minus b squared equals to 1. Okay, so that's another approach to getting the result. Okay, so two approaches, whichever you feel like algebraically. Okay, so that's part 1 of the question done. So now